Me too. I got some glasses in the mail.
I don't know. So just click start recording.
No, it's on her app, so
Oh, okay.
nothing you need to do.
Oh, no, that's a good thing. No, you don't need to write
I think so. So he'll definitely be judging you last week. He's a great
Okay, thank you everyone. Let's get started. Thank you everyone. I hope you can all sit down and pay attention. Cheers. I hope you've had a good week learning. Obviously, beginning a week one of a deep learning course is a pretty big deal, but I think you've definitely made the right move. So this is meant to be a tutorial session, obviously following on from Jeremy's material. So Jeremy's already done a week 0 and a week 1. So if you're keeping up to pace, you've gone through all the way through the week 1 material, the week 1 homework. Now what we're doing here is a bit of a recap. We'll spend an hour on the recap, and then we'll be getting more into group work and that kind of thing. All right. So this should be familiar to you. This is the Fastbook Jupyter Notebook. So something you may not have seen is these arrows here, like this, that I have. Forgive me with an unfamiliar laptop. To get an extension like this, where you can have an extra feature like that in a notebook like this, there's extensions you can do that I've put resources for in the Discord channel. So I think you'll get a lot out of upgrading your Jupyter Notebook along the way if you find little things to help you. So check out those extensions. So for example, NB extensions, they're not officially installed straight up, but you can turn these on and some of them may help you. All right, so welcome to your deep learning journey. The fundamental way that I'll measure, I guess, my success in helping you here is with traction. So the important thing is that you are getting faster and faster in understanding and applying these machine learning concepts and how to push through problems and that kind of thing. So that's how I'll be measuring success. Why is it a good idea to be starting this course right now? So deep learning is for everyone, for starters, which is to say, although it has been difficult historically to enter it, in that historically they used to require a PhD and that kind of thing, and the way to break into the course required a lot of kind of a long process of academia. Certainly that was the case for myself to a degree, in the sense that my personal history in getting into deep learning, I found it quite difficult with the initial study methods and ways of getting into deep learning. But the way this course is organized is structured to put us past that, which is playing the baseball rather than loading you up with academia at the front. So alternate ways to try to learn deep learning can be to do with reading a really thick textbook with more and more complex math, and that can just be harder and harder. So there's many ways to kind of fail to make progress in this if you study the wrong way. Another wrong way for me to study was trying to read paper after paper, and that just leads to more papers. Like, you never drink the whole ocean, right? One paper leads to more papers. So you have to find a balance in all this. That's just a few lessons from my personal history there. But suffice to say, you don't have to front load up with all this intense mathematics in order to get into this. You don't need as much data as you might think, because there are tricks. There are ways we can get ahead with our models. Stuff like pre-trained models can get us 99% of the way, right? And your particular use case might be that final 1%. So there's not necessarily as much of a data requirement as you might expect. And you don't need an expensive, massive hardware setup to get started either. Because we can create cloud resources, and you can deploy them exactly as you need them and tear them down exactly as you need them, you've never been more empowered to basically utilize the hardware that you need when you need it and then get rid of it. So you have the power to do deep learning, basically. And right now it's the best in the world in a variety of tasks. You can see some of them on the screen here in front of me. But these are big industry concepts, right? So there are so many products out there that don't yet exist in these fields of biology, computer vision, natural language processing, playing games, endless, that there are so many products that could be built with today's technology that you could build at the end of this course that don't yet exist, that you could make the best in the world at that niche. So really, if you build your skills up, your capability to create something amazing is there, because this technology is new, right? These are all pretty new world-leading applications for deep learning. So it's a good time to be getting into it. So a brief history of neural networks. I guess perhaps the thing to keep in mind is that this architecture that we'll be teaching you more about as we go, neural networks is, I guess, at the main core of the fast.ai library, so it's not the only kind of algorithm we can utilize. Basically, it has been shown that this is a completely flexible architecture in the sense that there's not necessarily this limit to what you can teach a sufficiently advanced neural network architecture. So there's something quite gratifying in knowing that our brains have that capacity to learn, in a sense, nearly anything, right? We will be fine. And so can, in principle, these learners that are based off this similar concept of the neuron. Now, primarily, it involves a process of a certain amount of inputs that have some kind of sensitivity to those inputs, an activation process like a firing. Maybe it's a kind of binary output, but maybe there's a kind of function there where there's signals to be interpreted. And then where does that output go? And so this builds up an architecture within our brains and obviously within our software. So over the past decades, you'd have read a little about this history of not quite understanding the limits and the possibilities of the neural network, but certainly there was some really solid foundational awareness of this hypothetical capacity, but not necessarily what was the main bottlenecks that needed to be destroyed, to be pushed through. So I'll just... So the thing I haven't mentioned here is a propagation rule for learning. So I was referencing before that process of activation based off inputs, but obviously there needs to be feedback in this system, a training process. So, and finally the 8th point there is that the system obviously is within an environment that is providing that feedback. So the history of neural networks has gone a long way over the decades, where generally the main breakthroughs that have come along have tended to be, obviously there's algorithm breakthroughs, but the hardware has grown spectacularly over the decades, and we've gotten GPUs and now TPUs, and the hardware will continue to grow and basically help us overcome the bottlenecks here. So let's see where we are. So, I'm not familiar with this laptop. My apologies, folks. Okay, so diving into Jeremy's approach to this game of how to learn deep learning. He talks about, I guess, what you might call this way of learning where it's like you're playing baseball and you gradually get better and better. And very early, you play the whole game. You learn the whole rules of the game, and it's a matter of iterating to get better. So whenever you observe complexity, and there's obviously complexity out there, don't be intimidated by how much there is to learn. It's just a day-by-day process for getting better. But one thing you do need to discover is nexus of information to help you deal with that complexity and discover more resources. So one nexus of information that I wanted to flag with regards to deep learning resources is Papers with Code, if you haven't seen it. So this is an amazing website. You can browse state-of-the-art papers and data sets, and in particular, I find this methods one really quite interesting, where it'll talk to you about all sorts of extremely important principles with regards to deep learning, or which is to say it has all sorts of categories and to check out there that will certainly come in handy later. That may be a bit too much for week one, but I just thought I'd flag that out there's certainly many, many resources to try to show you about deep learning and to communicate various concepts. So another one is the machine learning playground that Google has set up, which is an area where you can populate a region there with data and then train a model in a kind of graphical playground. So some graphical learners might find benefit to this in terms of creating a problem like having to discriminate these points, creating a learner graphically here with a certain number of neurons, and it's learned a function that is being displayed graphically for us for how to discriminate between these dots. So as you're beginning your journey here, you might find a little tool like this fun and handy to play with for figuring some of this stuff out. Okay, so you don't need a massively academic background to succeed. It's about playing the whole game and removing barriers and not getting stuck on any particular academic concepts. So there's a mindset basically for how to get through a data science project that I think is really quite important that Jeremy has flagged, which is you benchmark and check and you benchmark and iterate, and from that process you can destroy complexity. So that is effectively the main data science strategy to be starting with, to deconstruct any form of complexity, and I think that's a foundational mindset that he went over in chapter 1. But Jeremy also flags here playfulness and curiosity, and I do think that that's very important. So when you're reading someone else's really thick textbook of the concepts that you need to learn next, the trouble is you lose track of relevancy for what it is that you do really need to learn next. Whereas if your learning is being guided by your own curiosity and your own playfulness, you'll be specifically learning what you need to learn in that moment. through that self-guiding. So that is a way to really get the relevant information in front of you. So to do that, later we'll be doing some code play some code experimentation. But this is, you have to work with the code in order to discover various aspects of how things can go right and wrong. And that will be the relevant order for you to learn, basically, often enough, where you keep encountering, problems as they arise in your initial projects. All right, so the software. What are we talking about here? So Fast AI is trying to help us with PyTorch. It's trying to reduce the complexity of utilizing something that is enormously flexible. So PyTorch is built to effectively be able to create, in a sense, like any kind of transform in the end, and it offers thousands of types of transforms that you can stitch together, right? Basically, any software application in the end is something that's transforming input data into output, output to a screen or output somewhere. We're creating applications here where we're writing these mathematical transforms that's taking, value, shape, distributions, and sculpting them in the way that's necessary to ultimately declassify that data. We don't do all the hard work for this. Again, other people design model architectures that do, 99% of the heavy lifting and that kind of stuff. But ultimately, building up these perhaps quite intricate transforms involves PyTorch. So in due course, you'll be learning more about it, and it is a lot to chew through as you have a look at what PyTorch has on offer. I'll go across to, not that one, this one, the PyTorch documentation. So there's a fair bit here, and I think partly, I hesitate to use the word spare time, but from time to time, you want to give yourself the opportunity to do research before necessarily you encounter something in the wild. And so as you resolve to learn more about PyTorch, you can dip your toe in the water and having a look at what it has on offer here in its documentation. But ultimately, people try to make it easier. Effectively, often the most helpful thing that you can find in your journey to understanding something is someone's blog post that they've written about it. So here's an example, PyTorch to fast AI, bridging the gap. So, it's tricky indeed to, sorry, I shouldn't play up how hard things can be, but PyTorch as it is, there's a lot to it. And the point of fast AI is to reduce that complexity. So, often enough to get through a complicated process, it can involve finding blogs that step you through how to do something with a library, and you follow that, and then, again, that's your benchmark, and you iterate from there. So anyway, that is one example blog for helping you with the PyTorch to fast AI relationship there. So, so Jupyter, obviously, what we're working in here is the main development environment that Jeremy recommends, and so do I, primarily because your ability to iterate very quickly to measure if something's going right or wrong. You want to diffuse risk, you want to check things as fast as possible. So your ability to run code straight away in a cell over and over again makes Jupyter Notebook a good environment. The fact that it's quite customizable in so many ways is also part of that. Obviously, there are competing development environments, but I recommend basically following on from Jeremy's advice. So we've done our best to sort out basic setup stuff through the Discord. So I assume that most people have kind of gotten through all that. They've been seeing notebooks. They've been running some cells. So, and obviously by now, seeing differences in formatting, people would have encountered some data sets at this point, and learning a bit more about them and what it is that breaks the model. So I've run this first one here in the notebook. You can see where the error rate for this model, having trained on cat or not cat, is lower than 1%. So it seems like a powerful model. But all this code is in one blob at the moment. So we'll be deconstructing some of this code in the second half of the talk. But for now, you can see how this single blob of code has essentially done this A to Z, in a manner of speaking, of training a whole model from start to finish. You might think that this code is cheating in some way, that he's got multi-lines on one line and all the complexity is being hidden under the hood in some way or another. Now, there is a complexity being hidden away from you, but that's actually the point. The point is, it hasn't been hacked. This is how you can do it if you're at least utilizing a data set accessible to you that isn't particularly badly formatted. You know, it's not a raw data set per se, but he's not cheating. You know, all this is legitimate code. And if you look deeper under the hood at this code, you can see generally that the functions are not enormous, they're small as well. And the way he's able to achieve this excellent architecture design is through various very handy Python principles for architecture that are worth understanding, to do with constraining complexity within functions and within classes. And Jeremy refers to a paper about that, his Python architecture code that allows things to go so well. But yeah, we'll get back to that code. But now we'll stick with going through some of the principles. So we can see in the notebook, yeah, just showing a cat, showing a sample. An example functionality here is this ability to upload a file pretty easily and test that. And I hope everyone did test things that were cats or not cats. I think that's pretty sweet. And we saw in the Discord someone complaining that a lion was poorly categorized, but someone else showed that when you fine-tuned the cat detector with a few extra lion images, that it seemed to do much better. So an example of a shift of data distribution affecting the output of the model, and then the apparent ability for fine-tuning with extra data to fix that concern. Okay, but a point there is that you can embed widgets in the notebook to give you some extra functionality. All right, so what is machine learning? Obviously, we've all been talking about it a lot for a while, but you can see initially the very, very basic idea for an application is inputs, program, results that we're familiar with. As I was referencing before with regards to results out to a screen, but with a machine learning model, there's this concept that there's a trained part of the network, sometimes referred to as weights, but as Jeremy is trying to teach us the right labels for all our different words, we'll just be a little bit careful of semantics, but historically at least referred to as weights here. And so, yeah, as you can see from the diagram, the basic idea of inputs and the trained weights being part of an architecture that makes a model, that then you can create a prediction, measure the performance, and utilize a learning regime to update your weights. And from this basic idea where a model can check its own performance, it can therefore update itself so long as your data set is reasonable enough. Your data set describes the nature of what you're trying to learn well enough. So how do the weights get updated? through stochastic gradient descent tends to be the main approach. It's a very simple concept that ultimately will be going in more detail in the coming lectures, but it's effectively a matter of measuring what is the direction of moving this weight that would make the output that we want more likely. Let's do that. And you do that for all the weights in your network, and you take that very small step and you do that thousands of times or millions of times or what have you, and all your weights get trained, so through a training process. Obviously, there's all sorts of tweaks you can do to improve the training process, but that basic idea of stochastic gradient descent is that very simple concept that we don't want to get too complicated in our heads. So there are limits to machine learning that are worth discussing. Jeremy references here, well, you obviously can't create a model without having enough data, and so many of the, I referenced before, opportunities that we're wanting to have are dependent on you having access to data to create the model. And if your data has a distribution shift from deployment, obviously its usefulness is limited. So we need labels for our data as well to train it on the predictions, and labeling can be a very expensive process that often people underestimate how much time it can take. But there are tools that can help us for that. AWS tools, for example, Ground Truth is one, but there are other tools as well. So you can create feedback loops with your model if you release them into the wild, and then they impact what it is that they're managing. But I guess another example of a catastrophic disaster you may not appreciate is if your model isn't serving the needs of perhaps a minority group within the data set for which there aren't enough examples of. And so you might train a model that's very good for serving, say, one ethnic group but not others, and that kind of thing. So being aware of biases in the data is part of it, but also attempting to fix biases where possible. So this question of what are the limits of the data and what our model has learned is an ongoing challenge. And yeah, so feedback loops are one problem, but not having an overly biased system is another. All right, so Jeremy's going over here the import process, and I'm running behind in time. It's 6:30, so I'll
dive into some of the code.
Okay. Come on.
Did everyone get a chance to go through the notebooks and spend some time with the code, playing around with it?
Oh my God.
How many people tried, messing with the parameters, trying different data sets, stuff like that? Yeah?
Okay. Okay. Oh my God. All right, come on. Here we go. All right, so if you dived into the code, one way to approach it is splitting up code line by line. And so the first line of code in your notebook might be something to do with importing your library, but basically, anytime you do anything in data science, you also want to check what you're doing as well. So I would say to diffuse risk. So one thing I might recommend is putting out check statements there. You may wonder, what are these error messages that are coming up? I'll restart that and explain them in a moment. So just this first cell, I'm just making this point that you could check version numbers straight away. I've got another cell here. It's not necessarily relevant at the moment, but sometimes you'd have a cell setting your options for a notebook, right? So you may find that it's not printing all that you need, or columns for something aren't wide enough, or font size is wrong, and there's various ways to set those configurations. I posted in the Discord an example of an extension that you can put in that does a static code analysis. They're not always wonderful. You can see the static code analyzer thinks there's an error in the cell where you turn it on, in this case. So you'll get stuff like that you have to deal with. So if you want something like that, you can of course put in like certain errors to ignore and that kind of thing. But yeah, you'll get flooded with these little pink lines there that may help you. So especially if you're new to Python, a static code analyzer may really save your bacon. So we've created a path here from this untar data line. So we've taken the URLs that has come available through the fast AI import, and we've taken the ML sample, one of those URLs, and created. So how do we know what we've created? Well, a starting way to unpackage what you have is by printing the type. So that's pretty much one of the first go-to things you do before you might then discover the shape of something that you're working with. So if I'm just created a data loader, so in another line of the cell, a collaborative data loader is created from CSV, as it shows here, via this path call. Now there's a few bits going on here, so I'm trying to talk about a few things at once. One, you may see how to append to a path term requires this form of appending. And you might wonder why we don't just use a string, a simple Python string. And I can tell you certainly I've used Python strings for file paths plenty of times, and plenty of times failed to successfully import something because I'd introduced a classic mistake that these kind of classes help us resolve. So this path class is trying to help us not make classic mistakes in that sense. Anyhow, this is how you would append a file name to a path like this. So that gives us a Colab data loader. Now, one thing you can do from it is get a batch, but as I said, obviously getting started with this, you're just learning, well, what is a batch and all that. So a process for unpackaging it is printing out stuff like the type, and then once you have the type, splitting things up like this, for example. So this is a tuple. A tuple is a combination of multiple things stuck together in that sense, like as opposed to a list where the idea is you specify 100 things in a row. So we've got our X and Y from our one batch, but what is their shapes? Oops. Oh my God. Command Z. All right. So we're dealing with torch tensors, and we can see their shapes here and the first 10 terms of this particular tensor. And what are they? So this is X. So we have a bunch of integers here. So to look a little more at this data set at X, because there was a question that came up in the Discord with regards to the user IDs I saw. User noticed that when they were showing the results of a prediction, it showed a user ID of 43. But there was no user ID of 43 in the data. They imported the data into a data frame via this process here. This is short for pandas. That PD, you may wonder where that has come from because I haven't imported that, but that was part of the fast AI imports. So a data frame can obviously be displayed this way, and yeah, they found there was no user 43 in there. You can see how we can filter a data frame in this manner and then count the number of true or falses. Well, count the number of trues that are there, sum them, and that counts 95 rows where there's a user 73, but none where there's a user 43. So that was a question. And so to answer what the problem is, you can answer that by perhaps calculating a certain value will give you the clue you need for what's happening. So I'm printing up the top here. Okay, we've got 100 unique values which range from 15 to 665. You can see this print statement is just slightly more complicated, where I've put the variables inside the print statement like this that you might not have always seen, but Python lets you do that if you have this f prefix. So within this code, it's taking the length of the unique user ID terms in this data frame, and that's counting up to 100, and we're taking the min and the max as well. All right, but in the data set that is used for training, when we do something similar, you can see it's similar but not quite the same. The data set that I imported above, my way of referencing the user value in this case is like this, but otherwise it's the same kind of code. And our output's different, right? Now it's ranging from 1 to 100. So,
is there a copy of this notebook somewhere?
no, I just whipped this up while playing. But I can put one out there, sure. Yes?
Oh no, actually you moved ID count, sorry. I was wondering how you got this round bigger than the ID counts.
Yeah, so this is just counting the number of people for a particular ID, but it's not necessarily fully representative because it's just 50 bins and there's actually 100 people. So these histograms can be slightly distorting what is reality here, unless you're displaying it nicely. But at any rate, I think we've gotten the sense of what has happened, right? That we can see it now. So we had this question with regards to a particular user, but to see what happened, we had to step back and we can either calculate certain values or look at the data. And in this case, we can see that the data set has removed all the spaces between user IDs. So now, yep.
Someone on Discord just asked if you could make the window of the presenter a bit smaller. It's covering the notebook.
Let us see. Okay, I think so. Maybe like that. Yep. So the same column in the data set has been encoded to have a standardized range. So our models will overfit to noise if we let them. So we have to attempt to remove any particular pattern in there that we know isn't really signal. And so this is a standard concept where we've got some category that has these gaps in it, but the gaps are meaningless. And so if it stayed in the data set for the learner to interpret something from, it'd just be learning on noise. So part of the process for helping our models, of course, are these forms of standardization. In further lectures, we'll go into more detail for a lot of this data prep process. But at any rate, obviously what you should have been getting up to is training some models amongst it. Here's one for a collaborative learner, which fine-tuned for 10 epochs there, and we can see some results where it's, doing some predictions. But if your curiosity is driving you, you would then have trained another model, right? So to get to that next level, I would hope you would be curious, how can we get better results than this, right? Is there a model that I can train with different parameters that gets me there? And so if you're playing around, then yeah, you could punch in some different initial parameters for the model to train and train a new learner. We can see the scale of the learner here via examining the learners.model there. Perhaps our learner is too big and we can shrink it. So by Okay. So that one, its training loss is at 0.643 and its validation loss is at 0.71. And so next one, where we've shrunk this number of factors term down to 10, we can see the loss is worse. So it would seem as if it would be better to have higher n factors than the lower based off this small little round of experimentation. But so the Colab learner, though, I'm going to run some cells. The Colab learner, though, you can train a version where you're using a neural network rather than its default approach for this, which I haven't checked under the hood just recently, but it's probably a decision tree. Or I don't know. Do you know, Michael? What?
I'm not sure.
Okay.
What it is.
So there's more than one algorithm approach for solving a problem, obviously, and to create a learner that uses a neural network in this case, yeah, we'd have to specify non-default parameters. So here are those. This learner, you can see the training loss is much lower than the validation loss compared to this previous one. So what that would mean is it's overfitting. So what it thinks that it's learning in the training loss is actually learning noise, memorizing noise, worse than the learner up here. And so this would imply that part of the problem then is that the learner is too powerful and it has this capacity to memorize the data, and that you would want to shrink the learner or something. Yep.
I remember there was a conversation once that it's not quite overfitting yet. It's only if you run it a few more times.
Okay.
The validation loss goes worse, but the training loss goes down. But right now, both of them are going down. So if we run it some more times.
Yes.
Yeah.
Sam, just repeat the question into the mic.
Sorry, there was a very good point there. So it was pointed out that the validation loss for this learner 4 is still going down. And so it's not actually overfitting then, even though that the training loss is much lower than it. Because as long as the validation loss is still going down, then the model is getting better. That's a very good point. Sorry, I was focusing on examining the training loss there. So yeah, you could keep training this because ultimately it's the validation loss that's more important. All right, let's get back to Fastbook. Were there any more questions at this particular point in time? Okay.
Sam, do you want to pull up a picture of when to actually know if you're overfitting or not?
That's in here, yes. So there we are. So basically, you want the simplest answer that explains the data, but it's not a simple question of how complex a line should be in order to know that it's the ideal line, right? When you look at this example here, it seems obvious, a parabola, but to try to cater to all scenarios in this way, where you're both trying to learn something complicated, but you're also trying to not overfit to noise. So if your learner is too large and has the capacity to memorize your data, it can build unreasonably complicated explanations for the data, is the problem. And it's basically not at all hard to create a learner that is too large for the data set that you have. So one of the main starting points is the scale of your learner versus the data set that you're training on. But there's also many techniques around how do you, in a sense, try to enlarge the data that you're working with by perhaps augmenting it or creating artificial data or anything you can do to, in a sense, make it seem as if you have more data. And then effectively, overfitting comes from the problem of having finite data. if you had infinite data, the model, chances are, would have the capacity to learn the signal from noise. But it's the fact that you have finite data that now it doesn't necessarily easily have all the information to know when something's noise, and so it remains the big problem. Yeah.
When you're looking at the metrics of the training loss and the validation loss, what should you be looking for when they both go down?
So you're looking for, obviously, it'd be better to have a graph, but you're wanting the loss metrics to decrease as much as possible, but you don't want the training loss to get to this point where it's at like 100% accuracy on the data. I've had people pitch that the overfitted model that's getting 100% accuracy on the data can be better than the seemingly less overfit model that. So I guess there's maybe controversy there on whether it's allowed to have a massively low loss on the training loss and whether to just focus on the validation. But I guess primarily you want, you're trying to get the low point for your validation loss, and then there's a point where it'll gradually start coming up again, and you rewind and pick the point before that begins. Does that answer your question, Michael?
I think so.
Maybe someone else can explain it better, but this is one example of a demonstration of overfitting. But primarily coming from this idea of finite data with models that have the capacity to memorize. Okay, 6:47. So part of the main service that what Fast AI is trying to offer to us is a way to automate your training process. So the CNN learner here, it's part of the core of the library, because if you have to code your own training loops in PyTorch and code all sorts of fundamental parts to it, it's recreating the wheel, and it's a whole lot of drudgery and that kind of thing. So you want a higher level library that's taken all this power of PyTorch and combined it for you in useful abstractions, useful classes. And so that's the point of like the CNN learner, for example. It's trying to combine all this lower level stuff for you to ultimately give you this process for training, in this case, a convolutional neural network. So this particular line here, just to talk a little about what that's saying there, is it's saying, based off your data loaders, use the ResNet34 architecture to train a convolutional neural network learner, and use the error rate for the metric. So ResNet34 is a kind of architecture that is publicly available, and with trained weights for that architecture. So that can be downloaded in the background. And then to train one of these pre-trained models on your data set, it goes through a process of popping off the final layer, the head, to specifically train generally the final layers that are unfrozen on the task at hand. I'm sorry if that's sort of too much at once. We are going to be diving deep more into neural networks and how it all works as the weeks go by further. So I'll be giving some explanation here. We'll be explaining convolutions more in other lectures, but basically the main reason that we're using them for vision systems here, unlike some other data set where different features aren't necessarily related in an image, the pixels that are beside each other have a relationship. And so having this awareness of the nature of the data, we tailor the neural network to be specifically good at that, at understanding that kind of data. So that's why we pick convolutions typically for this kind of learning. But they've been so successful that Jeremy explains you can often convert so many data sets into an image-like form, and so use your convolutional learner even on stuff that you might not think typically of as being an image. So yeah, we use pre-trained networks to reduce the amount of compute we have to do. And so yeah, the process of using a pre-trained network that you've downloaded is called transfer learning, where you're taking some model with very, very good lower level weights, and then you're just training the weights towards the end of the network, and then you're just training the weights towards the end of the network that combine the features that have been taken out of the image into the abstract ideas of cat versus dog and that kind of thing, but you replace it with the classes you're training on, like tree and fence, for example. All right, 6:51. All right, I'll try to go faster. So in the low layers, it's learning stuff like straight lines and corners to recognize with these convolution filters. Basically, it can pass over the image a kind of likeness, so it determines how like a vertical line is this patch of the image. It does stuff like that for the low layers, and then for higher layers, it's detecting slightly more complexity, circles or squiggles, or the beginnings of repeating patterns. As you get through the network, the neuron that's receiving the information has a perceptive field that's wider in the image. So in order to classify a larger thing in the image, obviously that neuron has to have received information from those pixels, right? So the deeper into the network you go, the larger the perceptive field the neurons have, and then their role for recognizing these larger things comes there. So they're recognizing things like noses and ears. So there may well be like a face neuron in the network that decides whether or not to activate that there's a face based off, all right, there's probably a nose, there seems to be one ear, two ears, and that kind of thing. And it goes, all right, that's enough to seemingly be a face. So through these layers of abstraction and through that architecture, it works it out. But we'll be going into more on that later in the course. And here we see some of the examples of how you can transform data into image-based data and use a convolutional neural network upon it, for example. But you can clearly see how it would be possible to learn how to classify those images. And other forms of data becoming images, mouse motion becoming images, bytes of programs being converted into images. Our jargon, let's see, that's all fairly obvious. We need labels for the data. The architecture for the model is how the neurons connect to each other in a sense, as opposed to the trained weights themselves. So the architecture, is the template. The model, is the combination. So the process of training the model, often that's called using the fit command. And epoch is when you've gone through all of your data in one pass, and so two epochs is two passes and that kind of thing. The loss is the smooth measure of how the model is going. We need a way that is not noisy to train the learner so that the gradients that it's receiving for how to change the weights are smooth. So that's why it uses a loss, whereas we use a metric that's more meaningful to us. That might be something like accuracy or precision. The training set is what we set aside fully to judge the model and shouldn't be used basically to make any decisions for training the model, lest it poison the purpose of the data set. So we try to keep the training set completely set aside, and as Jeremy explains, it's a way to hold an external accountant, a consultant accountable or something like that, where if the person training the model doesn't even have access to the training set, that's one way to check on how well the model is going and that kind of thing. But that basically, to avoid disaster, you need a very good way of determining how effective your model is and whether or not it's working. And he highlights that for Kaggle as well, about how you have to synchronize up your basically your validation data set that you're using to judge the best model to the scores that you're getting when you submit that model to their validation data set. So yeah, if you're not accurately judging the success of your model, how far can you get? All right. So segmentation learning is one more task, but is handled fine by deep learning, and there's plenty of that going on. Text-based learning obviously is also supported by fast AI, and yep, hopefully there's plenty of people who will pick each of these data sets for their projects. How are we for questions at the moment, Michael?
I think mentors are answering questions in there.
Great.
Yeah, maybe we move towards the questionnaire.
Okay, yep, we're getting there. So that's the collab. Validation and test sets. So we use the validation set to make decisions about architecture for the model. There's more than one approach to that, though. Sometimes you can have a kind of dynamic validation set, such as you train the same model 5 times over, but use a different split 5 times for your validation set. So there's more than one approach. But always you try to keep the training set fully set aside. So Jeremy flags the importance of the how you can't always have a random validation set, particularly for time series data. You have to make sure that the validation set is reasonable, and often that might be that your validation set needs to be the most recent in time data for a time series like this. If you have data leakage, such as having a user in your training data who is also in your training data set and validation data set and your test set, like you'll have a data leakage basically, because it'll have seen the user before that now, he's no longer a user in the wild. So there's so many examples of data leakage where people fool themselves for how strong their model is, and so it's a very significant concern. Even the model can learn that a different camera is being used and that kind of thing to figure out how to cheat. Okay, we are at the questionnaire. We made it, folks. Okay, so I guess I'll just power through these now, unless we have extra questions. As we already established, we don't need lots of math or necessarily lots of data, because we can use pre-trained models and that kind of thing. We don't need lots of expensive computers. We can spin up computers that we need, and there are plenty of free options as well. And world-class models have been trained without necessarily more than one machine at a time. And you don't need a PhD anymore. The field has really opened up, so go for it. So machine learning is now the best in the world in so many categories, but we can see its applications in stuff like applied science, in terms of biology, in terms of playing games and robotic control, computer vision and recognizing medical problems, and obviously various forms of predicting the future and recommending, for example. What is the name of the first device that was based on the principle of the artificial neuron? The perceptron, I believe. And so it's like a one-layer neuron. What are the 2 theoretical misunderstandings that held back the field of neural networks?
Who knows? Who's going to answer?
No volunteers?
What question was this?
Number 5. What are the 2 theoretical misunderstandings that held back the field of neural networks?
Multi-layers.
Can I get a more specific answer than multi-layers?
Neural network couldn't solve the XOR problem in a single layer.
That's right. So a single layer neural network, there are certain things that it can never particularly learn. So that was one problem. Second misunderstanding is that having only 2 layers can now solve any problem, because it was shown that in principle, hypothetically, they had that enormous capability. In practice, that would sort of take infinite data if you don't have more structure than that. So it turned out you need more structure in practice with finite data than just 2 layers on average. What is a GPU? It's a graphical processing unit. It's it's quite helpful for parallel compute, and so that's what we need for lots and lots of weight updates. All right, so you've been running code for number 7 and number 8, and you, oh.
Just one question.
Mhm.
I feel like I've seen something called a TPU, which is I think a tensor processing unit. What is
Mhm.
that, and then should we be using it or anything?
Yeah, so Google has created the TPU,
Yeah.
and they've done it it's hardware that was optimized specifically towards this working with tensors, and so it is fast. You don't have to use any particular hardware per se, but you may find that using TPUs helps speed up your training. So it's a faster form of hardware than the typical past GPU. Of course, GPU systems become on many different scales as well anyway. But yeah, hardware will keep iterating and getting better. And so, yeah, Google is representing that the TPU is kind of the next generation GPU, as it were. Yes?
Would that, at what point will we be seeing FPGAs overtaking GPUs?
Well, I guess I don't know the future for hardware breakthroughs, but yeah, I guess I don't know. That's the short answer. Does anyone know the answer to that? No? All right, sorry.
You should repeat the question on the microphone.
When will FPGAs take over from GPUs in terms of hardware for training? We don't know. Okay, your question?
So the notebooks that you select at runtime, one of them is TPUs. Does that mean that we can switch to TPU and it would run faster? Or it doesn't work like that?
No, it does work like that. I think you're in a Colab notebook. Yeah, so changing the hardware for the runtime could speed up your training, yes. Yep, you're probably worthwhile doing.
Will it work? Does fast AI support TPUs?
That's what I was asking.
Oh, sorry, I didn't realize that was the question. Sorry. I don't know. I haven't used Google TPUs. Has anyone used a TPU for
I don't
fast AI?
think it will out of the box.
Okay.
I think, yeah, I'm not sure.
Okay.
JAX will. I don't think PyTorch will out of the box. Not sure. I'll have a look.
I was
Yeah,
going to
report
test it,
back.
but
Yeah.
since
Mm.
you're live,
Sure.
To do that and then see how it goes.
All right. Why is it hard to create a traditional computer program to recognize images in a photo? Well, because of how hard it is to write all the custom handcrafted rules that you need for that. So sort of the main power of this is, in a sense, having software writing itself in a way. You could pay a whole lot of people to attempt to write a whole lot of rules to classify something, but instead we have the software write itself to do that in a way by learning these weights. So we've seen the pictures of the machine learning models. Why is it hard to understand why a deep learning model makes a particular prediction? So perhaps in a similar way, it's hard to understand why a person does something, I suppose, because it's the summation consequence of all the weights in the network in the end, right? So there's many contributing weights to that final result. And so you can try to determine what was important about the prediction in various ways, but you don't get the whole picture at once, because ultimately you might have millions of things connected together. but there are tools that can help for feature importance, for highlighting regions of an image and that kind of thing that can help us with some of that. Name the theorem that shows that a neural network can solve any mathematical problem to any level of accuracy. Who can tell me the theorem? The universal approximation theorem, yes. So that's in theory, and that's, I guess, in a sense, based off you having infinite data, as it were. What do you need in order to train a model? Well, you need hardware, you need data, you need labels.
PhD.
You don't need a PhD. You don't need a lot of expensive upfront stuff. You don't need lots of math. And then, yeah, obviously you need your architecture and a process of updating those weights through training. And did I miss anything about that? How could a feedback loop impact the rollout of predictive policing models? Well, certainly they have done. Yeah, if your model is predicting where the police will be and then it tells them where to go, then you'll create a feedback loop. But I think perhaps it's also very hard to spot data leakage as well, to notice when something's a proxy for something, where an address is a proxy for poverty or something like that. And so you think it's learnt from a feature, but maybe really it's using this proxy in a way you didn't anticipate. So there's many ways that a model can go wrong. All right, do we always have to use a 224 pixel image? Who knows?
Or we do have to resize them because it's retraining on that specific size, and we have to use something of that size or something.
So you don't always have to use it depending on the type of model that you're working with. Historically, models were quite strict on that. More modern models have ways of transforming inputs down. If your images are coming in of all kinds of different sizes, you're always going to resize them to something. But the main reason you don't just use any size is because of the computational cost. So there's a huge constraint with regards to how much your model costs to compute. So you pick the size that makes sense for how much information your model needs to solve a problem versus how expensive it's going to be to be using that model in practice, is what ultimately guides that size selection. What is the difference between classification and regression? Classification is a category output, whereas regression is the prediction of a continuous number. In order to know that something has been classified, it has to cross a threshold of some kind that you choose, and you have a certain power there with how you choose that threshold if you want to be, if you want to err on the side of caution, for example. It's 7:10 now. Do I stop streaming soon or just try to power through?
Let's finish these off and then we'll move into groups.
Okay, all right. So what is the difference between the validation set and the test set, and why do we need them? So the training set is what the model is looking at to update its weights. The validation set is the set we're using to make architecture choices and to judge the model, and it hasn't had access to the validation data, but we have access to the validation data for our choices, whereas the test set is what we're using for the final judgment of the model's strength. We're trying to not use that for any of our choices at all in order to have an impartial measurement of the strength of the model. So we're trying to avoid any kind of data leakage from the test set for any choices that we make.
Sam, actually on that, given that we've still got 12 questions left, how about for the rest of the questions? Let's break into groups. We'll answer them in groups of, let's say, I'm going to come up with a number out of my head, 6. Let's do that. So let's go through the questions as a group. Maybe you want to actually let me hop on the mic.
Yep. Thanks, folks.
Yeah.
Week 1.
So thank you, Sam. So we do have some AI in this machine. Excellent. So, so I think for the rest of the questions, obviously everyone in here, we can all sort of shuffle our chairs and join smaller groups. Everyone online, we've obviously got the channel for this week's lesson, but there's also some chat rooms where you guys can hop on the mic as well. So I think there's only a few there. I can make a few more now, but for anyone who is watching online and is in the Discord, definitely hop into some of those groups. I think there's a couple things that we want to do. Because it is the first week of the course, most of us don't know each other that well, and so I think before we go through the remainder of these questions, and I'll leave this on the screen so that everyone can read them, before we do that, let's hop into our groups of 6, and then I want you all to ask each other a few questions or go around the circle. We're not going to stand out and catch each other and do team building exercises, but we're obviously all here for a reason, right? We all want to learn machine learning. There's probably a problem that we want to solve, or a general area that we want to apply this technology to. It could even be that maybe you just want to make more money so that you can provide for your family. So whatever the reason is that you're here to do this course, when you get into your groups, I want you guys to introduce who you are, what you do. A lot of you probably don't work in technology. A lot of you probably don't code day to day. So, give a little bit of background into what you do, why you're here, what are the types of problems that you want to solve, and, maybe what's something cool that you've learned so far, or what you're looking to get most out of the course. So let's do that. Let's spend no more than 10 minutes talking about ourselves, because we don't want to do that. Then let's go back through and answer the rest of the questions, okay? So if everyone could get into groups, everyone online, feel free to hop into one of those channels. No more than 10 minutes. So it is 7:12 local time, so at 7:22 our time, we'll get back to the questions. So make sure that you tell everyone your life story in that time. I will keep an eye on the chat for those of you online. Chat to you soon. I might even actually hop into one of those online rooms. So either chat in the lesson channel, or if you do have a mic, hop into those mic rooms. Cool. Chat soon.
Like, is it for the people online there?
I'm going to have a chat to some people. Long and annoying. Anyway.
So it's been that years.
Because I've collected some data, so want to be able to go back and find so when this goes
They're taking their time.
How'd you go, Sam? Good.
It's a bit different.
Yeah, I like that you went over the notebooks. That's always good. And it's good to give them coding examples like before practical. Did you upload that by the way?
Not upload my little
Put it like up to there so you can reference it.
Okay, that was a good part, yes.
Yeah.
Okay, so maybe better than
Yeah, and then just give that I guess it's different to slides, like they can have front end open a bit, or you can have it with blank stuff and you write code in, and then write code with if they want to.
Well, I always wanted to. I wanted to have a
Yeah, you gotta do like a quick high level summary. I guess they've got like this section. It's a careful balance.
That's what I thought. And like all the issues with
This project is like,
Yeah, exactly. I knew that was if I finished it. It's like,
All right, guys, let's finish our introductions. Do you guys want to start going through the remaining questions? I think we were up to question 19. What is the difference between classification and regression? So if you guys want to start going through them, I think what we might do is in around 15 minutes, we'll come back together as a group, and I would love to do some Q&A with you guys to hear how we can best serve you guys and give you the most out of the course. So take 15 minutes, blast through those questions, and then we'll come back together in 15. Sound good? Okay. Test. All right. Hello, everyone. Hello, hello, hello. Whoop. All right. Hey, guys. Hello. Sorry. Hey everyone. So it is 7:41, and I think I hope everyone's met someone new tonight, and we all feel a little bit closer, a bit more squishy. It is early in the course at the moment, and it is, look, I wouldn't say it's a slow start, but a lot of us have already familiar with some of the stuff that we've talked about. So because we don't have any group projects yet, we've got a little bit of spare time tonight, and I think given that we've got another 8 weeks of the course to go, I'd really love to just do some open Q&A and really understand from you guys, how can we best serve you as a group of mentors and organisers so that you can all get the most out of this course. So already had a chat, obviously, with some of the people here about, what they'd really love to learn. So I know that all of you definitely have 1 year of Python, because obviously you wouldn't have signed up if you had less. I'm kidding. I'm sure many of you have less, and I'm glad that you still signed up anyway. But I'd really love to understand, what are you looking to get most out of this course? A lot of you already do deep learning. You already use fast AI. So maybe you're here to, get a bit more insight from maybe some of the mentors or some of the other people in the course who have experience. So I think there's a few questions that I have. One, what's the thing that you're most looking to get out of this course? Is it intuition about, when do you try different models, or what's the way that you actually go about doing a machine learning project overall? Secondly, I think when we think about the structure of the course and these sort of sessions, how can we best do these? So let's start with the first question. So, and this is just open. Feel free to shout things at me. Don't throw anything, but please say things. And definitely in the channel as well. I'm keeping an eye on the Discord channel. What are you guys looking most for out of these sessions, particularly these in-person sessions? And how can we make sure that you're getting the most out of it? So, if it's the presentations, what do you want to see in the presentations? Is going back through some of the concepts that we talked about, worthwhile? Do you really want to focus on the questionnaires? Do you want to see us work through code on the screen? What do you think is going to be most useful?
Can we do work through code on the screen while we do it as well?
Yeah, for sure.
Because doing it, I think, is really important.
Cool, I like it.
Simple stuff, even if you guys provide simple data sets that when we, on the computer, we can download, type along with you, for example, data sets that are not already in the Fast AI course. Because I'm, I don't know about you guys, but I don't have a lot of time, and I'm sure there are people here that have been through pretty much the whole course already. Right? I ain't got time for that. So, data sets that not everyone's seen, that we can do some fun things with.
Yeah. Optimize your homework time, right? Yeah, perfect. Cool. Yeah.
All right. Well, I've been using fast AI a bit for a couple of years now, I've had some results good enough in all that people continue to pay me to use it to do stuff. Which
excellent.
Is nice. But what I'd really like to get out of this, other than meeting a ton of crazy interested people in the room, is just a deeper knowledge of the library that enables me to know how, why, and when to implement my own architecture, my own novel architecture for something, and have some kind of intuition of why it might work. So content that emphasizes that is going to be really what I'm after.
Cool. And just for everyone online, the question there was content around how we can, know when to diverge, implement custom things, and sort of how to make those decisions, how to do it, stuff like that. Cool. Anyone else?
I like to learn the things that aren't going to work in AI, like you.
I've got lots of those.
Don't even try AI on that one. Yeah.
Cool. So is because when you're first starting out, you've done toy problems, you don't necessarily know what it is in the wild. People always say data is so much worse in the wild, but you don't really know what that is firsthand. Is maybe some content on that outside of the course going to be valuable? And how do you actually go about a project? How do you develop that intuition? What are the sorts of things to think about, the decisions to make, stuff like that? Is that something that you guys would like to hear about?
Yeah,
Okay, cool. Maybe we can do it at the end of one of the sessions. Have a bit of a short session.
A bunch of the cloud platforms have SaaS offerings and AI and so
Mm-hmm.
forth as well, and that's a good point to start. But I would like to know kind of when do you need to start looking at building stuff like this, as opposed to leveraging maybe a managed service?
Cool. Don't say it too loudly because I'm sure a bunch of AWS people bust through the door. Just kidding.
Typically jump straight into custom building stuff and they don't necessarily.
Yeah, sure. And I think right now, like, a couple of years ago, some of those solutions weren't that mature, and you sort of hit the edges pretty quickly. But these days, there's some great solutions there, and particularly some of the automated systems are excellent if you want to solve a problem quickly. So maybe we can do a session on, what are some of the ones that are out there, when might you go between each of them, and I guess where do they fit, where don't they fit? Yes, so the questionnaire was about cloud platforms. Where do platforms like SageMaker and some of the other cloud platforms fit into the toolkit of a machine learning engineer? So we can definitely cover that.
So we've got a lot of people here that already work in ML AI, and it'd be cool to hear from them what they do with it.
Mm-hmm.
Kind of related to what doesn't work, I guess, but how people are using it.
Yeah, sure.
What are they doing?
Sure. So I think one thing too from all the mentors, so that you guys get to know them, I think before every presentation it'd be cool, hear a little bit about them, but maybe they can share a quick 5-minute project that they're either working on now or have worked on, some of the challenges that they had that you wouldn't know unless you were working on it. And we just time box it, you get a little bit of insight, and then you can go chat to them about it later if that works. Cool. Sounds good. Any others?
I was going to say it'd be good to, there's a lot of mentors floating. It'd be good to have somewhere to look up what their areas of expertise are. So if you have a question, you can DM.
For sure. So I think we should do that. So maybe all of our mentors here and tuning in online, maybe we can all, put a bit of a summary of some of our areas of expertise. I might be a bit light, so I have to think a bit harder, but maybe we can put that in. And if anyone online or here wants to chat, feel free to. Cool. I'm just having a look online. Some clarifications for specifics from the code can be useful. Anything that we couldn't quite catch in the reading. So I think as mentors, if there's something that we understand there's a little bit more to it, that's, as we work through the code itself, maybe that's where we pick it apart and try some different things. Some microphones placed around the room would be a great idea. I'll have to figure out how we do that logistically, but great idea. Some end-to-end workflows using fast AI. So sounds good. Cool. All right, and I think today there was a couple examples, like overfitting, for example. We talk about it in the notebook up here. Time series is actually very interesting. I could lecture a lot on that and how not to do it. But there was something in the book here about overfitting. I think there was a diagram. I'm just trying to figure out where it was. Here we go. But there's a bunch of different videos and images that really well summarize how do you know when you're overfitting and what to look for, and blog posts. So I think too, for us as mentors, as we're working through the content, if we see that, we'll try and touch on the things where we can really add, something else, or point you guys to other blog posts that'll be really useful to dig into. Cool. All right. Anything else on that?
I was going to ask, you touch on anything around MLOps, so governance of models and data sets and training?
Yeah, so it's not covered in the course, and I think as far as production goes, in this Fast AI course, it's really just based around can you expose your model as an API endpoint and then tie it together with a a fairly simple sort of front end UI. What we can do is we can touch on sort of what the world of MLOps looks like. It's quite dynamic, it's moving really quickly, and it does get into a lot more of the engineering side of things. So this is, more focused on how to build models and how to work with data. A lot of the MLOps side, even if you go into the real world in companies, a lot of companies will punt it over the fence to the engineering team, and hopefully they can figure it out. It is becoming more integrated these days, where people sort of own that end to end. But maybe a little bit later on in the course, we can just sort of give a bit of a lay of the land of what things are looking like, and if you did want to upskill in that area, what are some of the tools or platforms that you might look at to future-proof yourself. Maybe sound good? Cool. All right. So
if you do have any other ideas or things that you want to share, just put it in the lesson 1 chat, because there's already some in there. So I'll go back later and sort of summarize those and, basically share that with the mentors, and we'll try and integrate that into how we run these lessons. The other thing is, so these 2-hour sessions, so, if we think about, I think there's obviously been some points in there about how we can make the best use of this time. Later on in the course, not next week, but the week after, we will start on group projects. So at that point, probably the second half of each week is going to be sort of group work. But in that first hour, it sounds like, maybe 5 minutes for an intro to the mentor and, a project that they're working on, sort of 10 minutes to go over the core concepts in the book, build on anything where there's additional content that we can add, and then spend most of that time really actually going through the code, playing with it, other examples like a lot of the great stuff that Sam put together, which we'll share after this talk. Does that sound like something that would work really well for you guys? Cool. Anything else that we should add in there? Excellent. Great. All right. Awesome work, team. I think we've got it's been a little while since we last ran this, and I think if we can iterate quickly in these first few weeks, we can make sure that everyone gets a lot out of this course. So I just want to say thank you for, this is a group thing. So thank you for everyone contributing, and we'll take that on board and make this better and better every week. So thanks so much, guys, and thank you for joining. Cool. That's it.